Okay, now we want to consider different kind of loading, that in a case that we have a distributed load or we have a couple moment, right? In this case, again, we can still use Heaviside. In fact, Heaviside in this case is better using Heaviside compared to the conventional method. Consider this simple again beam fixed to the wall, and then we have a distributed load. Let's see, use for example yellow or maybe kind of red for distributed load. There we go. And let's say this is 1K. I just put unity 1 here, the top, and the length are given as from here to here is 1 meter, here to here 1 meter, and this beam is fixed to the wall. Now the question is find, let's see right here, the question is find V of x, or the equation for deflection of the neutral axis when x is taken from either left or right. Let's take x from the left. This is a nice color, we haven't used this, turquoise. So let's say this is your x at any point taken from the left, and we want to find the deflection of this curve, equation of deflection. Alright, well, what is the procedure to do that? Well, the first thing is to find wall reaction, and once you get the wall reaction, then you can just cut it at any point like x and use Heaviside function to find the moment distribution in just one line, right? Don't forget, the trick is one liner approach to make your job easy. Otherwise you have to waste your time, right? That's the reason we use Heaviside. So then once you get your moment relation, then you double integrate it to get the deflection. Okay, so let's do that. Let's first find the wall reaction using basic vector statics method. So if I take this guy as my system, let's go back to the old thing. So this is my system, and then I draw FVD right equation, solve them, and then verify them to find the wall reaction. So you're gonna get, if this point is A, B, C, you're going to get AY, MA, the wall, and then you're gonna get, replace this guy with this single load at its centroid. And the magnitude is equal to the height, which is 1 times the base, which is 1. So the magnitude is 1, and the location is obviously 0.5 from here. 0.5 from here. It's at the center. Why? Because this distributed load is uniform. It's rectangular. The centroid is exactly in the middle. And from here to here is 1 meter. So now, using this, I can find AY and MA. Summation of 14y is equal to 0. So AY is equal to 1. Okay? And summation of moment of what? A is equal to 0. That would give me MA positive, negative, 1 times 1.5 is equal to 0. So your MA is equal to 1.5. These are the reactions. Okay? So let's go back to the beam. So let me draw my beam again here. And also let's cut it at the point X, as you can see here. Let's go back to this beautiful turquoise color. So let's cut it here at the point X from the left. And don't forget that when we want to use Heaviside function, we try to cover all loading up to the very end of the beam, right? So this X should be extended as I extended it to the very last point just before point C. Okay? Then if I do that, then I have 2 different cuts. One on the left and one on the right. So I go ahead and draw them. you have one cut on the left, and this is the part on the right. Okay, now you're going to get a distributed load as we had before. So you're going to cut this distributed load here up to this point. So you cut it somewhere in the middle of the distributed load, or some point inside the distributed load. So some part remain on the left and some part remain on the right? And also you're going to get AY, which is basically 1, and MA, which is basically 1.5 on the left, and the magnitude of this is 1. And then also you're going to get internal loading here. Let's say this is point X, right? You're going to get the MX this way and shear load this way. On the right system, you're going to get opposite VX and opposite MX. So this is a full free body diagram for two systems resulting from the cut at point X. Now what I'm trying to say is, like the previous example, you see this one on the right, you really don't need to worry about it if you take the one on the left, and vice versa. So it's your choice. You either take it from the left or from the right. Now what I do, I use the one on the left, as you can see here, because it includes all the loading, the war reaction, a part of the distributed load. And don't forget, from here to here is what? X. Now I'm just ready to go ahead and write summation of moment equation for the system on the left and find the internal moment relation. So let's do that. Summation of, so let's call this system 1, and this one on the right, system 2. That I'm not going to use it. Okay, so in system 1, summation of moment about point X is equal to 0. So let's expand this equation. The first thing you get is mx right here, positive or negative? Positive. Then you go to Vx. Vx is 0. It doesn't have any moment because it passes through point X. And then the next kind of loading is this guy, is a part of the distributed load. Again, is a part of the distributed load. It's not the entire distributed load, right? So in this situation, I want to replace this with a point load. Don't forget that. You cannot put this from the beginning, replace it with a point load, and then for the moment diagram, just use a point load. You get some sort of jump. We already discussed this before without using Heaviside function. Now I'm not going to repeat it again because you already know it. When you want to draw a moment diagram, you should not replace the distributed load with a point load when you want to draw the moment diagram. You have to consider the distributed load, and after you cut it, then it becomes external load to each system. Then after you cut it, then you can replace it with a point load, exactly like the way I'm doing it right now. And you have done this before in the previous chapters you covered in class. So right now we want to focus on the Heaviside function. So here I'll replace this with the point load at the center. There you go. Okay, so now I ask you the question, what is the magnitude of this point load? The magnitude is height, which is 1, times the bottom. The bottom is from here to here. What is that? That is equal to Heaviside x minus 1. See? This distance that I put in a bracket is Heaviside x minus 1. It's not x, it's not 1, it's not 2. Because look, we are cutting a part of this distributed load. Look at here. A part of this. It's not half of it, it's not 1/3 of it, it's just a part of it. So if from here to here is x, from beginning to end is x, and from here to here is 1, then this area, this length from here to here is Heaviside x minus 1, right? So what is, back to the question, what is the magnitude of this point load that I'm going to replace it? Well, the answer is the area under this part of the distributed load. The area is the top, which is 1, times the base, which is Heaviside x minus 1. So 1 times Heaviside x minus 1 is just the magnitude of this load. And what is the point of action of this point load? At what point should I put it? Well, the answer is the centroid of this part, which is from here to here, which is what? Heaviside x minus 1 divided by 2 at the center of the base. You see? So if I want to add its couple moment to my summation of moment, to this equation that I'm just trying to finish it, it's going to be mx plus the magnitude of the force times moment arm. Moment arm. So what should I put for the magnitude of the force? You can see that that point load is 1 times Heaviside x minus 1. And what should I put for the moment arm? Heaviside x minus 1 divided by 2. Positive or negative? Well, you take your right hand and you see this is going this way, so this is positive. Okay? So this was the tricky part. Well, then the next thing is this load. You see, we're moving from right to left. The next load that I have to include in the moment relation is the 1K force at the wall. So the moment coming from that is simply negative 1 times x. I don't want to use Heaviside because that wall force is always there. I don't need a switch to make it on or off. Okay? And then I go to the couple moment in the wall, which is simply plus 1.5, and that's all, is equal to 0. So what is my moment relation? Solve this for mx. Mx is equal to, take those stuff to the right, half of x minus 1 square. You see Heaviside x minus 1 multiplied by Heaviside x minus 1, result is Heaviside x minus 1 square, times half, and because it goes to the right, it becomes negative. And then you take the negative 1x to the right, then you get plus x. Again, this iPad thing is not collaborating with us. So you get positive 1x, which is x, that's the reason I don't buy anything from Apple or Microsoft. It is not designed for us. So plus x, negative 1.5. That is your moment relation. Remember, if you don't want to use it without using Heaviside function, it's going to take you more than this just one-liner approach. Now I want to find deflection. So what should I do? Well, the relation for deflection was EI times second derivative of deflection is equal to m of x. Now again, assume E dot I is 1. Right? Then you get the second derivative of v is equal to m of x. Plug m of x, double integrate, apply constant of integration, and then you get your equation of deflection of the neutral axis. Right? So the second derivative, let's do that. The second derivative of v is therefore is equal to mx, which is negative 1 over 2 x minus 1 square plus x negative 1.5. Okay, the first integral gives you dv dx, which is your theta slope, is equal to negative x minus 1 to 3 over 6 plus x2 over 2 minus 1.5 x plus c1. Again, you apply dv dx at x0 is 0, the slope is 0, then you get c1 0. Go ahead and apply one more integral, to both sides, then you get v of x is equal to, so this goes to negative 1.24 x minus 1 to 4 plus x3 over 6 minus 1.5 x2 over 2 plus c2. Again, you apply v at x0, 0, then you get c2 is equal to 0. So there you go. This is my equation of deflection. Look at this equation. This equation is a fourth order polynomial. So your deflection is more complicated than all examples we previously covered. Now if you go to this case right here, if I want to draw this curve, if you draw it on computer, this is going to go down like that, and then you have a more complicated plot. So it goes down. Now you can evaluate this at any x. Okay? So this was just another example that shows you how to apply the Heaviside technology when you have a distributed load, especially when you have a uniform distributed load. Now let's go to another example right here, and I want to give you an example that you have a couple moment. You may ask, well, I already know how to include point loads, distributed load. What about couple moment? Let's say again this is your beam, and you have a couple moment here, 3 Newton meter. How can I use Heaviside function to describe the moment relation in this beam with just one relation? Well, the answer to that is, again, we do exactly the same thing. First, we find the Wall reaction. In this case, the Wall reaction is simply another couple moment that cancels out this 3 Newton, so the entire thing remains in balance. And again, in order to do Heaviside, the procedure is cut it from either left or right. I do it from left, and try to move your cut point to the very, very right part of the beam such that include all the loadings that you have, and take this as an X, right? And then draw your FVD, write your equation, and simply apply Heaviside. For if a function needs a switch, then apply a Heaviside, and there you go, that's all. So basically everything is consistent. You don't need to memorize different rules when you have different loading. So let me draw the FVD for this system right here. So this is the cut from the left, and this is the cut from the right. Again, don't forget, we don't need anything from the right. The reason that I'm doing it is just to show you how these two systems are related together. So at this here, right here, you have a mx, and then you have an opposite mx on the one on the right, and here you have a vx. I'm keeping the positive direction, default positive direction. And then for the system on the left, you have this 3K couple moment, 3 Newton meter couple moment here, and another 3 Newton meter, but the opposite direction in the wall, to keep it in the balance. Don't forget, here we don't have a load, okay? And here, the last thing I want to say, from here to here is x, and from here to here is what? The entire length, which is the entire length, say, if we get equally spaced point from left to right, then from here to here is 1 meter, from here to here is 1 meter. That means if this is x, the one on the right, let's use green now, the one on the right is 2 minus x, which we really don't use it, don't need it. I just wanted to show it to you how it works, right? So let's focus on the one on the left, right, summation of moment about point x0, and then find internal moment. Summation of moment about point x on system left is equal to 0. So you get positive mx, and then you go to Vx. Vx doesn't have any couple moment because it goes through the x. And then the next thing is this couple moment right here. Now here is the interesting thing, in fact the tricky thing. You want to include this 3 Newton meter couple moment only when your x is greater than 1. How can I do that? Well, you just make Heaviside function like a switch. You just say 3, the magnitude of couple moment. Obviously, it is a negative value, okay? mx is positive, 3k is negative. If you take your right hand, then you see it's clockwise, and then it's a negative value. So negative 3, but you want this negative 3 to disappear when your x is less than 1. So you say multiply by x minus 1 and put power 0 here. So what happens here? Just consider this term. This is very important. When x is smaller than 1, that means we are right here, this here. We don't have a couple moment here. When x is smaller than 1, this term, in fact, is 0. Although mathematically 0 to 0, so is not defined. 0 to power 0 is singular point. But according to definition of Heaviside function, if you go to part 1, the definition was this is a null. That means nothing exists there. So it becomes 0. So automatically this negative 3k couple moment at the middle will disappear when your x is smaller than 1. And what about if x is greater than 1? Look at this term. When x is greater than 1, let's use a different color. Here. If your x is greater than 1, then the end result of this is x minus 1. And inside parentheses, and to power 0 become 1. So 1 times negative 3 is just a pure negative 3 couple moment. So this term, in fact, acts like a switch, like a switching mechanism. That means it includes that negative 3 when your x is greater than 1. And it just eliminates that negative 3 when your x is smaller than 1. So let's put it together. So let's go back. So you get this Heaviside function to power 0. Okay? And then the next thing that I want to include is the couple moment 3 in the wall. What should I write? Well, I simply write plus 3 because this doesn't need a switch. It's always there. Regardless of whatever your x is, that 3 is always there. Okay? So you simply say this is equal to 0. And then you solve for mx. Moment at x is equal to 3 Heaviside x minus 1, 0, negative 3. Okay? So let's draw it before I want to find the deflection. I know that if I plug this relation into the second derivative, double integrate, apply boundary condition, I find the equation of the deflected beam, right? But just for the heck of it, let's plot this relation. In order to plot this relation, I say, well, let's evaluate this when x is between 0 and 1, and evaluate this when x is between 1 and 2. So when x is between 0 and 1, what happens to this term? We already talked. When this term becomes 0, so you get negative 3. So if I want to draw my moment diagram, this is m of x, and this is x, right? From here to here, your moment is pure negative 3. What if I go x greater than 1? Well, this term becomes parentheses x minus 1. Because you have power 0, you put it here, so the entire thing becomes 1. 1 times 3 minus 3 becomes 0. So your value of the moment diagram is, in this from here to here, is entirely 0. So that's your moment diagram. So negative 3 from 0 to 1, and 0, pure 0 from 1 to 2. Okay? Now let's find the equation of the deflected curve. Again, assume E dot I is 1. Okay, so because the I, you can easily use method of vector static to find moment of inertia. You can easily get it from table E modulo elasticity depending on type of material, and then you can compute this just a constant, just take it 1. That's not the point in this example. So if you have this relation, the second derivative of deflection is equal to mx over EI. If your EI is 1, then you have second derivative of V with respect to x is equal to m of x. Plug m of x, so you get second derivative, let's show the derivative with dot on V to make it simple, is equal to m of x, 3 times x minus 1 to 0 minus 3. Integrate, first integral, you get V dot is equal to 3. Now this is the thing, if you take integral of that, treat it like parentheses. What is the integral of x minus 1 to 0? You get x minus 1, you raise the power to 1 divided by whatever the power you raise. Refer back to your calculus book and then you get all these techniques. So in fact that becomes 3 times x minus 1 Heaviside to 1 divided by 1, negative 3x plus c1. Apply the boundary condition at 0, then c1 become 0. Take one more integral, then you get v at x, that's what I'm trying to get, is equal to 3 Heaviside x minus 1, 2 divided by 2 minus 3x2 over 2 excuse me, plus c2. Again, by the same token, c2 after the applied boundary condition becomes 0. So that's your equation of the deflected beam. One-liner approach. So in the next example, I want to consider a case that has many different loading. So you can see that I'm going to give you one problem, and you can see that if you don't do it without Heaviside function, which I'm actually asking you to do that, it's going to take you a while. So that's the subject of the next video.